All right, so I just want to take some new notes here. We're going to talk about free fall today. We've talked about free fall before to an extent, but we're going to add a little bit more detail. And we'll talk about terminal velocity as well as air resistance. So there's a couple new elements to free fall that we haven't explored before. But let's get started. So the first slide, all free falling objects fall with the same acceleration. Okay, so that is g, as you recall, hopefully, which is roughly 9.8 meters per second squared. However, freely falling objects aren't what we see most of the time because there's generally some kind of force opposing an object falling freely. But anyway, they all follow the same acceleration because the net force on the object is only its weight, and the ratio of the weight to mass is the same for all objects. Not the best explanation. It'll make more sense in a couple slides, I promise. Galileo showed that falling objects accelerate equally regardless of their masses. This is strictly true. It's always true if air resistance is negligible. In other words, if you do it in a vacuum, like the video we saw earlier in the year where they dropped a bowling ball and a feather, and they fell at the exact same rate. So it's always true as long as there's no air resistance or air resistance is negligible. It is approximately true, so it's almost true, when air resistance is very small compared to the mass of the falling object. So the bowling ball, the air resistance on the bowling ball wasn't that big compared to its mass. So when air was present, the bowling ball fell much quicker than the feather, and probably the acceleration due to gravity was approximately 9.8 meters per second squared. So it was approximately true for the bowling ball, but not for the feather, because in the case of the feather, air resistance is not small compared to the mass of the feather. In Galileo's famous demonstration, a 10-kilogram cannonball and a 1-kilogram stone strike the ground at practically the same time. The experiment demolished the Aristotelian idea that an object that weighs 10 times as much as another should fall 10 times faster than the lighter object. So, obviously, Galileo did an experiment with two different mass, kind of similar objects, a cannonball and a stone, and saw that they fell at approximately the same rate of acceleration. So, if you recall, mass, which is the quantity of matter, and weight, which is the force due to gravity, are proportional. The weight of an object is mg. So a 10-kilogram cannonball would experience 10 times as much gravitational force as a 1-kilogram stone. It has 10 times the mass, so the weight will be 10 times as much, and the weight is the force that gravity puts on an object. So in Newton's second law, F here would be the weight. So it tells us to consider mass as well. So if we're looking to find the acceleration of an object, we take the force and we divide it by the mass. So a 10-kilogram cannonball has 10 times the force, so that F gets 10 times bigger, but it also has 10 times the mass, so that gets 10 times bigger. And if the top and bottom of that fraction get 10 times bigger, then really nothing happens. You get the same acceleration. So that is sort of the mathematical explanation of why everything falls at the same rate. Heavier objects or more massive objects have a greater force of gravity, but they're also more massive, and the two cancel each other out. So an object in free fall is acted upon only by the force of gravity. Again, free fall means there is nothing opposing this thing falling. So we are ignoring air resistance. There is no air resistance. So in free fall, there's only one force, the force of gravity, which is equal to mg. So the force is mg, and the mass is m. You can see doesn't matter what you do to the mass. If the mass gets bigger, it still cancels out. So whatever the mass is, it's always going to cancel out, and the acceleration is going to be g. So the conclusion here is that the mass has no effect on free fall. Again, free fall means there are no forces opposing the object's motion. All right, looking at the experiment, the Galilean experiment mathematically, the weight of a 1-kilogram stone, of course, is 10 newtons if we assume gravity to be 10 meters per second squared. And if we go to calculate the acceleration due to gravity, the force acting on that stone is its weight, which is 10 newtons. To find the acceleration, we're going to divide the force, its weight, by the mass, which is 1 kilogram. So 10 newtons over 1 kilogram, and that gives us 10 meters per second squared, or g. If we do the same math for the 10-kilogram cannonball, the force on that cannonball is its weight, which is 100 newtons. And of course, to find the acceleration, we're going to take that force, divide by the mass. So we're dividing 100 newtons by 10 kilograms, and we end up with the same 10 meters per second squared. So again, in free fall, everything falls at the same speed because the force acting on the object is proportional to the mass of the object. So why does everything fall with the same acceleration? What I just said, basically the force acting on the object is proportional to the mass of the object. And when you divide force by mass, the mass in that equation basically cancels out. All right, the next part is about air resistance. Falling and air resistance. So the air resistance force on an object depends on the object's speed and area, right? So get into more detail here. A feather and a coin fall with equal accelerations in a vacuum, but vary unequally in the presence of air because air resistance acts differently on the feather than the coin. So when falling in the air, the coin falls quickly while the feather flutters to the ground. The force due to air resistance diminishes the net force acting on the falling object. So air resistance is an upward force that's resisting the motion. It's like friction. It kind of is. It's the object pushing through the air. So when forces of gravity and air resistance act on a falling object, it is not in free fall. Free fall means nothing opposes the motion of the object. When air resistance acts on a falling object, it opposes that motion. So technically not free fall. Speed and area. You experience the force due to air resistance when you stick your hand out of the window of a moving car. Think about that. I'm sure you've done it before. As the car speeds up, the force on your hand increases. You can also notice that the area has an effect. In other words, if you hold your hand flat so that the smaller side of your hand is facing the oncoming air, you'll feel a certain amount of force. And if you turn your hand so your palm faces forward, now the air has a larger area to act on. It pushes on the palm of your hand instead of the side of your hand. You'll feel that the force increases. So speed has an effect on air resistance. Obviously, the faster you go, the more resistance there is. And area also has an effect. The more area that's facing the oncoming air, the more air resistance you're going to feel. So this isn't a useful equation. It's more of an expression. Air resistance force, the force due to air resistance, is proportional to how fast you're going and the frontal area. In other words, the area that is facing the oncoming air. So when you turn your hand sideways, there's a smaller area facing the oncoming air than when you turn your palm facing forward. The expression shows that the air resistance force is directly proportional to the speed and frontal area of an object. It also depends on the density of air and lots of other things. So on a colder day, the air is denser, you'll feel more force. On a warmer day, the air is less dense, you would feel less force. So there's a lot of factors here, and we're not going to quantify this exactly. A couple new concepts here. Terminal speed. This is the speed. Remember, speed doesn't include direction. So speed is generally the magnitude of the velocity. So the terminal speed is the speed at which the acceleration of a falling object is zero because friction balances out the weight. Terminal velocity is the terminal speed along with the direction of motion. If you're a falling object, your direction of motion is always going to be down. So no big surprises there. So it's important to emphasize that zero acceleration does not mean zero velocity. Zero acceleration means that the object will maintain the velocity it happens to have, neither speeding up nor slowing down. So the context that we're talking about is a falling object. When an object begins to fall, there's basically no air resistance because, as we said, air resistance is proportional to speed. As the speed increases, the air resistance increases. And that air resistance force, the force due to the air resistance, is an upward force. It's resisting the object falling. As the object falls faster and faster and faster, eventually the air resistance gets so big that it's equal to the object's weight, which is the force pulling the object down. So if you have an equal force pulling down, the weight, and an equal force pushing up, air resistance, then the object will not accelerate anymore. The net force is zero because the up and down forces cancel each other out. So when the up and down forces cancel each other out, that's what we call terminal velocity or terminal speed. You speed up, you speed up, you speed up until the air resistance is so big that it cancels out your weight. And then the object would continue to fall at that velocity, whatever velocity it was that produced enough air resistance to cancel out the weight. So a falling object will speed up quickly at first, and then the net force on that falling object gets smaller and smaller because the air resistance force gets bigger and bigger until it finally completely cancels out the weight. So skydivers reach terminal speed when air resistance equals weight. We just kind of said that. Terminal speed just means you're not accelerating anymore. You're not going to speed up or slow down because the upward and downward forces acting on you are equal. Therefore, you're in equilibrium. So you'll fall with a constant velocity, but an acceleration of 0. Falling feather reaches its terminal speed quite quickly. Its area is large relative to its very small weight, so air resistance has a large effect on the feather's motion. It has very little weight, so it doesn't take much air resistance to cancel out the weight. It has a very large area, so the air resistance on it is fairly large because of the large area. A coin has a relatively small area compared to its weight, so the coin will have to fall faster to reach its terminal speed. The coin probably weighs as much as the feather, but the area is much smaller, so the air resistance, the force of the air resistance will be much less. The coin will have to fall much faster before the force due to air resistance is equal to the weight of the coin. All right, so the terminal speed of a skydiver varies from about 150 to 200 kilometers per hour, depending on the weight and orientation of the body. What does that mean? You ever watch movies like where people are skydiving and they want to catch up with somebody else who's skydiving? They always, they point themselves downward like they're diving, and that does make a difference. That's like turning your hand with the smaller side facing the wind. You have a smaller frontal area facing the oncoming air, and that means your air resistance will be less. So if you jump out of a plane looking like these guys here, flat, you're presenting a large area to the oncoming air, and you're going to reach a terminal velocity that's slower than if you did a dive, basically dove straight down out of the plane. That would be less area, and you would actually have a faster terminal velocity. So a heavier person will attain a greater terminal speed than a light person. Obviously, body orientation makes a difference. We were just talking about that. There's a good example of body orientation, the flying squirrel. It increases its area by spreading out, like the skydivers in that picture before, and that increases the air resistance, which decreases the speed of its fall. So that squirrel has a large frontal area in that position, so it will not have a very high terminal velocity because the air resistance will be pretty large because of the large area. So it won't take a lot of speed for the air resistance to cancel out the weight of the squirrel. Here we go again. Terminal speed can be controlled by variations in body orientation. A heavy skydiver and a light skydiver can remain in close proximity to each other if the heavy person spreads out like a flying squirrel, while the light person falls head or feet first. Parachute greatly increases air resistance and cuts the terminal speed down to 15 to 20 kilometers an hour, which is slow enough for a safe landing. So why does a parachute work? Well, it has a huge area. So that huge area increases the force of air resistance, which decreases the speed required for air resistance to cancel out the weight. At low speeds, air resistance is often negligible. Air resistance is actually proportional to the square of the velocity, which you don't really need to know, but it's interesting to note that, if you double your velocity, you are quadrupling the air resistance if nothing else changes. So at low speeds, air resistance is you can kind of ignore it. It doesn't have a huge impact on free fall. But at high speeds, it makes a huge difference. In perfect free fall, an object would accelerate indefinitely. It would always just speed up by 10 meters per second every second that goes by. But in real life, everything has a terminal velocity. It'll speed up to a point, but eventually it will reach a velocity where the air resistance is equal to the weight and it doesn't speed up anymore. So down here, if you hold a baseball and a tennis ball at arm's length and release them at the same time, you'll see them strike the floor at the same time. They're not going very fast. Probably take less than a second to fall. They don't get any faster than 10 meters per second. In this case, the air resistance is fairly negligible. If you drop them off the top of a building, however, you're going to notice the baseball is going to get there first. The two balls are about the same size, and so the air resistance at a given speed will be about the same. However, the baseball's heavier, so it has more weight pulling down on it. So if they're experiencing similar air resistance, but the baseball has more weight pulling down, the baseball is going to accelerate faster. It's going to get there first. All right. Here we got a photo, or this stroboscopic photo shows a golf ball and a foam ball falling in the air. So a golf ball is they're similar in size. The golf ball's heavier. The foam ball's very light. So the weight pulling down on the foam ball isn't very large compared to the air resistance. And you can see that as time goes by, the foam ball is kind of falling further and further behind. So this is like T equals 1, T equals 2. These are all taken at the same time. You can see the foam ball is getting further and further behind because the acceleration isn't as great, because the net force isn't as great. And let's see. So, which experiences a greater air resistance force, a falling piece of paper or a falling elephant? What we're looking for here is, of course, the elephant has a greater frontal area and falls faster than a piece of paper. Both of which mean the elephant pushes more air molecules out of its way. That's kind of what's happening with air resistance. You're pushing the air out of the way, and that takes some force. The effect of the air resistance force on each, however, is another story. So obviously the elephant's going to fall faster, despite the fact that it feels more air resistance. Its mass, its weight is so much greater that, the weight is still far greater than the air resistance, so it will fall faster. A heavy person and a light person open their parachutes together at the same altitude, and each wears the same size parachute. Who reaches the ground first? The heavy person is gonna get there first because the light person reaches terminal speed sooner. The heavy person continues to accelerate until a greater terminal speed is reached. So, if they have the same size parachute, the parachutes are going to resist their falling with the same amount of force, but the heavier person has more force pulling down, so they're going to be going faster. So what forces determine air resistance? Force on an object, the speed that the object is traveling, as well as the frontal area of the object affect the air resistance. And that's about it for this section. So you're just going to do the homework from the book that I posted and submit that on Google Classroom, and that'll be it. Let me know if you have any questions.